Okay, so hi again. Hope everybody slept well. Oh, this starts working. Okay, so today we will still be talking about random graph coloring. So let me just do something like 5-line recap of what we did yesterday and what we should somehow remember from yesterday. So we are still talking about random graph coloring, meaning this Hamiltonian over all edges of the graph. And these are all pot spins. And let me draw here this kind of a, when the number of colors Q is large, we had this kind of a behavior here. This is the average degree, the C is the average degree of the graph. Then we argued that up to average degree, that is something like 2Q log Q. A random graph can be colored with Q colors, and beyond that it cannot be colored with Q colors. Yet if we look at algorithms that actually do it, we could easily find algorithms that do it up to Q log Q. So here it was impossible. Here it is easy. And here we don't know still what's happening. Somehow algorithmically it looks hard. So that's what we will be trying to understand today. So that's when Q is large. When, we will also be talking about cases like Q3, 4, etc. But it's slightly different. And I will be commenting on that. So one of the things that we defined yesterday and to which I will be comparing today is this annealed entropy, which simply was the logarithm, the expectation of the number of colorings of a given graph. And the expression we got was logarithm Q plus average degree half logarithm 1 minus 1 over Q. Okay. And then we also define this quenched entropy, which is the same thing, except that the expectation and the logarithm are switched. And what is this? Okay, so our goal was somehow to compute the typical entropy. And in order to do that, or starting to do something like that, in the second part of the lecture, we derived this belief propagation, which was designed to compute this partition function on a typical graph. Well, we so far computed it on a tree. So let me remind what were the equations that we got for graph coloring. So we had this message xi indexed by a color S, going from node I to node J. So I always draw this kind of picture to somehow help understanding what this message passing means. This would be the node I, this would be the node J, this would be the node K. So this guy updates with some kind of a normalization and a product over all neighbors of I, but not J, of 1 minus the same message as K to I, where the Z is defined as sum over S of the same quantity. So yesterday I wrote this belief propagation much more general, but when you think just about graph coloring, actually the interpretation of this equation is quite natural. This can be interpreted as a probability that the node I takes color S in the absence of the edge between I and J. Okay, and then you think about it. If you condition on the color of I and this edge is not present, and you're doing this tree approximation where this branch is independent from this branch, then the probability that this node can be colored by S must be proportional to the product of probabilities that these guys are not colored by S, right? And that's the product, and the probability that I am not colored by S, since this is the probability, is simply 1 minus that. Okay, and then this term is there just to normalize it properly, such that it is indeed a probability. So this equation actually comes quite naturally. And somehow, maybe you're used to think, say, about, maybe it's useful to comment how is this related to some kind of a mean field equation that you could write. Right? It's not very different from some kind of a mean field. If you were writing some kind of a mean field equation for this kind of graph, you would just take out of the node and then compute the field these neighbors are creating, and that would be somehow what would be playing on that node. Now, here we are doing almost this, but we are putting away one of the neighbors. And why is that? Well, because if we were not putting it away, then you see, so basically there will be some correlation that is created due to the fact that these three guys are connected via this I, that we would be approximating somehow crudely if we were writing the mean field. Whereas here, if we really condition on what is this color, S, and if we put one of them away, then this somehow has the chance to be more correct than the mean field. And now we will be arguing, is this really correct or not? Like we argued that if it was a tree, that means indeed there is never ever any connection here and here, it's really separate branches. Well, then this is just an exact thing. And with the derivation that we did yesterday, you could persuade yourself of that. Okay, so let's start studying this equation. Oh, okay, no, last thing. Okay, what is the expression for this z? So what we derived was, from this, we also derived expression for the partition function. I didn't write the partition function, but the probability distribution on the proper colorings, that's just like this thing, e to the minus h. And so this would be the belief propagation, and the BP or beta, as you want, expression for the logarithm of the partition function would be written like this. So it's a sum over all nodes of logarithm of okay, let me write term like that, and minus sum over all edges, a logarithm term like that. And let me just write what these terms are for coloring specifically, because yesterday I wrote them for this generic problem. So this SI, that's very related to this normalization here. We say J, that is around I, 1 minus psi S J to I. And this guy is sum over S, or rather for coloring I can write it like this, minus psi S, and this guy goes from I to J, and this guy goes from J to I, and this would be just 1. Okay, so this is our expression. Let me separate it a little bit, the expression for the beta free energy. So let's start doing some, and this is the belief propagation. So maybe are there some questions about that? So this is from yesterday. This maybe I didn't write explicitly, but this is when you take the generic expression that I wrote yesterday explicitly, and you specify it for this Hamiltonian. And then you evaluate this expression at a fixed point of these belief propagation equations. So So in general, there are, this belief propagation, you can think about it in two somehow very different ways. Like you can think about it as an algorithm. So you really, you encode the graph in your computer and then you implement these iterations and then you initialize them in some way, you iterate them, you look for a fixed point, then you find a fixed point, then you do something about it. So what do you do with the fixed point? So for instance, one strategy to find proper colorings in random graphs could be what people call decimation, because you get some probabilities here, right? So probabilities are not really setting colors. This is just the probability over all coloring that this node takes a given color. So what people do, they decimate. They would just choose the node where these probabilities are the most biased, where one of the elements is very large. And then they would set this node to that color and reduce the graph. Remove that node, its edges, and remove that color from the list of the colors its neighbors can take. And they will rerun the belief propagation algorithm again, choose the node which has the largest bias, fix it in the color of that is in the direction of that bias, and go on like that. And that's a pretty good algorithm. I mean, for instance, here let me do also one little axis, what's happening as an average degree when we have 3 colors. So yesterday we wrote that the average degree at which the annual entropy goes to 0 is something like 1.42, was it this? I hope so, something like that, yes. Now, if you do like some numerics, you will see that the colorability threshold is somewhere at 4.7. And this belief propagation decimation algorithm is not so bad. It works something like up to 4.5, something like that. And when you look in the math literature, and you look what's the algorithm that you can analyze rigorously, that works the closest to this colorability threshold, it will be a work by Dimitri Aklioptas and Chris Moore, and it works up to 4.03. Okay, so this one, is just an algorithm that you can run and see numerically. So, okay, maybe this is good. So this is like down here is the analytic, and fully rigorous results. And this would just be, so far, this would just be the result of, numerics on large instances. Say on, n is, say, I don't know, what you can do in practice, 10 to the 5, 6 graphs. Graphs of 100,000 nodes, million nodes. It's a sparse graph, so if you do some kind of simulation like that, it's quite, you can go to sizes like that. So just to have a picture of what's going on. All right. So let's start refining that picture. What is really this number and what's going on here and what's going on here. So I was saying, you always look for fixed points of these equations. So can we guess at least one fixed point of this equation for the graph coloring? So can you see that if we just plug that psi s psi s is equal to 1 over q for every s and for every edge, and we will call this the uniform fixed point. Can we persuade ourselves that this is indeed a fixed point? Right, so let's just plug it in. Let's just plug it into the right-hand side and see if the left-hand side fits, right? So let's do it. So on the right-hand side, we have 1 minus 1 over q power, whatever is the degree of the node I minus 1, and we need to divide by the normalization. And the normalization is the same thing, but q times. No, everything is the same. So obviously it fits because these things just cancel and we just end up with 1 over q. So this is indeed always a fixed point of this equation. Right? Okay. Right? So some people say yes, but what about the others? No, it was a bit harder to wake up for the others. Okay. So what do we do with the fixed point? We want to compute this beta entropy to see what it gets, right? That's what we are curious about. Like, is it different? You know, we had this annual one, which was this really naive estimate. So this one should be better. So what does it give? So let's plug it in, right? It's easy. We have the expression here, so let's plug it in. So let's see what's the, so let me call this the S beta. S beta, actually 1 over the N. Okay, so what's the S beta? So it's 1 over N. So the first term will be sum over all nodes, logarithm of the Zi, was the Zi. That's again Q times this term 1 over 1 minus Q power, and this time is degree of I without minus 1. That's the first term. And now the second term is sum over all edges. Or again, logarithm. 1 minus. And here I have sum over all colors, right? So this S goes from 1 to Q. And here I have 1 over Q, and here I also have 1 over Q, because this is this uniform, where is it? This uniform fixed point. For every Xi, I'm plugging 1 over Q, right? So I have 1 over Q, Q times, so it is all together, it's again 1 minus 1 over Q. Okay, so what is this? So first of all, here, you know, nothing, you know, only thing that depends on I here is the di. So let's just factorize this logarithm. So we see that this Q, that just gives me log Q. What about this term? That just gives me 1 over N, sum over I 1 to N, di log 1 minus 1 over Q, right? Minus, oh, did I forget? Maybe I forgot a big bracket here, because the 1 over N applies also to this term. Minus 1 over N, sum over all edges. And log 1 minus 1 over Q. So we see that these terms are similar, right? Actually, nothing here depends on the edge. So what is this? So we just need to count how many edges we have, right? If you remember, the number of edges in the graph is just the average degree times the number of nodes. And because every edge has 2 ends, divided by 2, right? So the number of edges is this. So this accounts for C half, the average degree half. Again, this doesn't depend on di, so this we can put out of the sum. And then this is exactly the average degree, right? By definition, that's the average degree. So we have this logarithm 1 minus 1 over Q times C minus C half. So altogether, this is just log Q plus C half log 1 minus 1 over Q. So that's the beta free energy corresponding to this uniform fixed point. So you are far away, you don't need to walk like 10 meters to see that this is exactly the same thing as here, right? That's exactly the annual entropy. And we already argued yesterday that this cannot be right, at least not up to the colorability threshold, right? Because the colorability threshold is strictly before this expression goes to 0. So this cannot be right. So does it mean that all we did, you know, all this horrible derivation that was on half of the blackboard, that is useless? So of course it doesn't mean that, otherwise I wouldn't be doing it. Yes, questions? Well, we are, you know, what else do we want to look at? If these equations, you know, if you want to interpret these equations on a graph, you know, on the tree, the nice property is like you just run it once from the borders to the leaf, to the root, sorry, And that's a fixed point. I mean, if you run it again, you get the same. If you update it again, you get the same thing, right? So there you really don't have this notion of something that is not a fixed point and something that is a fixed point. Now, if you want to, if you start thinking how to interpret these equations on a graph that locally looks like a tree, but it is not a tree. It has many loops on, on distance that is bigger than logarithm of the size of the graphs. It actually has exponentially many loops. So everything is somehow connected to everything, unless this average degree is ridiculously small. But you see, it's not so small. I mean, we are not talking about average degree that is like half or something. We are really more, Q log Q gets quite large. So we want to look at a fixed point to somehow have this this relation, on a tree is what it was a fixed point. Here it's a fixed point. I mean, it's a, it's equation that need to be satisfied, because you see, if you don't look at a fixed point, then you somehow compute these from these, but then these you compute them from their neighbors, so this will not hold anymore. So looking not at a fixed point would not really make more sense. So we do want to look at a fixed point, but maybe not always at this one, right? The fact that this is a fixed point doesn't mean it's not the only fixed point. So that's where the trouble comes from. So, okay. So let's see. So what can get wrong? So first of all, there can be other fixed points, but then this fixed point doesn't even need to be stable, right? The fact that something is a fixed point doesn't mean that if I perturb it, it actually stays a fixed point. And these fixed points that are not even stable under perturbations, they are probably not interesting either, because physically they will correspond to something, not stable. It will be something marginal from which any kind of dynamics will go away immediately. So why would we be looking at this? So a first thing that we may do that may give us some hint about what's going on is to analyze the linear stability of this fixed point under this dynamical process, right? So what we will do, we will write, okay, let's now work with some, yes? Can you repeat it? I don't hear you.
So 1 minus 1 over 2 is also a fixed point?
1 minus 1 over q is also a fixed point? Is it? I don't think so, because if you plug here any constant different from 1 over q, then you just have something powered degree, you have something powered di minus 1, and you have the same thing here, but the sum here will give you q. So the only way to make it consistent is really to make it 1 over q. So indeed, it's a good question. I mean, you could ask something slightly. You could ask, okay, let's look for a fixed point that is the same for every ij, but that is different. Is there something that would differ on the colors? This would somehow give us just like one equation of q variables, not twice m equations on that many on q times that variables. But in this case, you would actually not find anything. It's something that could lead to something interesting in other kind of problems that really actually, for instance, require magnetization. But in this ferromagnet, this is the only kind of a fixed point which is the same for every ij. Okay, so this is not helping. Okay, but let's look at this stability. So let me erase this. So now we know that S beta. So now let's write it here, that this is also equal to the S beta of the uniform fixed point. So, uniform fixed point, but also let's think about it, what it means physically, right? I mean, if this is the magnetization of the pot spins, this is saying that the magnetization is 0, right? If we just had two colors, it means that with probability half we are in one, and probability half we are in the other. That's precisely what we mean when we talk about a paramagnet. Right? So physically, this would actually be the paramagnetic fixed point. So I may not write uniform, but let me write the beta free energy of the paramagnet. Paramagnet. Okay, and then I can erase this because this was just like a little calculation.
If you do this on a tree, that this actually is the correct partition function? Or graphs which are things.
Yes, so if the boundary condition of the tree is 1 over q, then this is the correct partition function, as it must be, because whatever you put on the boundary, what the BP gives you on a tree is the correct result. So but we will get back to that. We will go back speaking about trees with different boundaries. But let's first speak about the linear stability of this guy. So let's consider that the psi s ij is equal to this plus some little perturbation. And I must just be indexing the perturbation in the same way, right? Because, okay. And epsilon will be something small, not necessarily positive. So it can be negative, positive, it's just the perturbation. And then what we will look at is how stable is that dynamics. So when we talk about dynamics, let's write the time here. So this will be t plus 1, and this will be t. Okay, to make it explicit in which way this is a dynamics. Okay, so this is a calculation that actually, not for the coloring, but for the spin glass model, has been done by David Thales in '86. So the Thales that got the Nobel Prize this year in physics. But it's also a calculation that on trees has been done by Kesten Stigum, mathematicians that were studying Galton-Botson branching processes, which is nothing than a name for a tree that has a degree distribution that is this Poisson degree distribution. Okay, so you can think about the tree as a branching process, and that's something that people studied in mathematics. There was, I believe, like 60-something. 60s. I don't remember exactly if it was 66 or 61, but long time ago. Okay, so it's kind of a classic calculation that's instructive. So let us do it briefly. So what do we do? So if we need to linearize this equation around that fixed point, so that if the epsilon is 0, then this is a fixed point, so that we can write something like epsilon s. You basically do the Taylor expansion. So let me call this something. Some function, right? So this will be some function curl f that depends on the messages that go in. So all these messages that go in, where k is in the same set, neighbors of I but not j, okay? And then here basically what we need to compute is the partial derivative of this function that depends on these messages. Let me write it depends like on all the vectors. So I will, just to make it clear, I will write the index here differently of k to I, where the k are always the same things. Okay, and it's a partial derivative, say with respect to epsilon. So apparently, okay, r. Let me write t here. Whatever, not t is time. R as v. R. And one of them, right? So one of them. And okay, one of them. So I should not call this the same one, because otherwise it's not the same one. Okay, fine. And here epsilon r k to I. Right, so this is just the generic, this is just the first order of the Taylor expansion of that equation, so that's always the linearization. So I really haven't write anything here. So what we need to do is to, it's the Taylor expansion, so I need to evaluate it when the epsilon, epsilon psi, I need to evaluate it when the psi is equal to 1 over q. Right? When you do the Taylor expansion, here is the perturbation, and the derivatives, you are evaluating them in the point around which you're expanding. All right, so all we need to do is compute the derivative. Cool. So let's see, what's the derivative? So this partial f with respect to CR ki, and remember that I can write these indexes in the S, that's kind of the indices that play a particular role here. So what is this? So we need to look here. So it's easy, we just have two terms to make the derivative. So one of the terms, let's keep the 1 over ci to j, and then we have this product. So you see that only here we have the indices L, but only one of them will be equal to K. All the other ones, they will just stay there. So I say, so the product over L that is a neighbor of I, but is not J and not K, that will just stay there. So what were the indices? S and L to I. Okay. And the last guy that indeed has the L to I here, there's the guy with respect of K to I here, that's the guy with respect to which we are making the derivative. It will be there, but only if S is equal to R. Right? And it's 1 minus that, so it will create a minus, but it will also be only there if R is equal to S. Right? And that's it. Okay. And then the other term, in the other term, we will make a derivative of the Z. So this will be, it will be minus zi to j squared. Then this term over there will, we will just copy it, and then we make a derivative of the z. So this term we just copy it. Okay, well, L, j 1 minus L to I. Who do I call them already? S. And now we make a derivative, so this, okay, we make a bracket. And now let's make a derivative of the z. So you see the z, it's again a related thing, but since we are summing over all s, for sure one of them will be the r, and the other ones will not be the r, so the other ones just go away, right? So here I don't have any delta rs, I just have this product over the L that is around I, but not K and not J, of 1 minus xi from L to I S. And then I also have the minus that comes from the derivative of this term, because there is a minus here, so that changes the sign here. Okay, that's it. So the derivative is done. So now we just need to plug in the fact that xi is 1 over q. Okay, so let's go. So the minus stays there. So maybe, the z is here several times. So let's see what the z is when xi is 1 over q. We already wrote that, right? When this is 1 over q, the z is just q times 1 minus 1 over q di minus 1. Okay, so c. So this is 1 over, so q, 1 minus 1 over q di minus 1. Then there is the delta rs. And then there is this thing, which is also 1 minus 1 over q to some power. And this time is di minus 2, because here we were removing 2 nodes. One because that was the target node, and the other one because that's the one we derived. Plus, here we have the same thing. Di minus 1, but all that squared. And here we have 1 over q di, because this one we didn't derive. And here we have the same thing, but power di minus 2. So we see that things somehow simplify, that basically all the terms that have di go away, so that's reassuring, nothing will depend on the I anymore. And so what are we getting here? We are getting delta rs divided by 1 over. Did I? Yes, here is minus 1, thank you. So, minus sign where? First term. Which one? Oh, I forgot the minus. Yes, you're right. I forgot the minus. So that's, and here we are getting plus q squared here. And what is left from these factors? Just 1 minus 1 over q here, right? Okay, so it's, so it's a simple expression that depends only, that doesn't depend anymore on the I. So here, a priori, it could have depended on all these indices I, j, and k, which it doesn't. So okay, that's nice. And on the indices r and s, it depends, but in kind of a simple way. So this is like a little matrix T RS, right? And this is its expression. Fine. So what do we do next? So we know exactly what is this. So this is, oh, did I forget the sum? Oh, I forgot to sum here over the R, right? Right? Because these are vectors, so I need to, so the perturbation in each direction matters here. So I forgot the sum here, because now I would be missing it, because here I have the T, okay, let me call it SR just to keep the notation somehow reasonable. K to I. Oh, and okay. Both of the sums, I actually forgot that. I also should sum over all the possible K, right? Of course, not only about the R. So these Ks, I also want to sum over them, because I perturb everybody. So this perturbation will depend on all the K, because all the neighbors are perturbed. Okay, now it's the right expression. Okay, and so how do we go about it now? So these are how the perturbations evolve. But now we said they go in both directions, so they are, positive, negative, and if we somehow computed an average of this, well, then this would average to 0, because epsilon averages to 0, and these are just linear terms, so this would average to 0, and this is not getting us anything interesting looking at the average, because these are alternating terms. So to see if the perturbation is growing or decreasing, we should really look at its variance. The average is 0, that's not interesting. But what about the variance? Is the variance decreasing or increasing? Yes? ES, yes. Here? No, that's R, and I'm summing over the R. The perturbation in direction S depends on all the other directions, a priori. And I'm keeping the sum over R here, and that's what somehow makes this a little... Exactly. So eigenfunctions, that would be the direction in which this perturbation goes. But we look at the eigenfunctions, yes. But, okay, let's of what, right? Because we have this matrix Q by Q here. So this is a Q by Q matrix. And then we have this linear operation here. And if you look at that, well, that's also some kind of a matrix, and we will actually talk about it more tomorrow. It's a really interesting matrix. But it's a matrix that has size that is the graph, right? So, okay, we will be talking about that tomorrow, but if we can avoid that, that will be good. So let's try to, let's try to avoid it. So we want to look at the variance. But now these perturbations, they are independent. If we square this term and take the average, which is what we need to do when we look at the variance, the cross terms, where the k is not equal to L, well, average, they will be 0, because these things are independent. So all that would matter will be in terms of this sum, it will be only the squares. So just to write it down, so let me write it, the variance of epsilon I to j will just be, I just want to write it, it will be, I don't want to write it very formally, so just like hand-wavingly, this will depend on, this will basically be summed as many times as I have neighbors, and then, there will be this matrix T squared, and then there will be the variance of this, say that would be the T plus 1 thing, and that would be the T minus 1 thing. Oh, T thing, all right, and K to I. So this is a matrix now, and this is a vector now. So what will matter for the stability will be just the growth factor of this thing, and that will be the average number of neighbors minus 1 that I have. And maybe that is a tricky, but for the Poisson degree distribution, if I choose a random edge, the number of neighbors on one of the end of the edge, on average, is still the average degree. right? On a regular graph, it would be the average degree minus 1, because I removed one of the edges. But the Poisson has exactly this property that if I condition on having at least one edge, then the conditional distribution of how many neighbors more I have is still the Poisson. It's kind of a particular property of the Poisson. So the average degree and the average branching factor of these Poisson trees is the same, right? Whereas for regular trees, you see that the degree is the branching factor plus 1. But for the Poisson, it's the same on average. So this is just C. And this is a little Q by Q matrix squared. So what will matter is its largest eigenvalue. So let's just call lambda t. Lambda t will be the max eigenvalue of t. It's computed in a moment. Times this variance of before. So the condition for this uniform fixed point being stable, so stability, we get it if and only if this c lambda t squared is smaller is smaller than 1. So the critical fixed point will be, okay, let me ask this. So I will define C stability as 1 over lambda t squared. Okay? So that's it. So the only thing we need to do is to compute the largest eigenvalue of this little Q by Q matrix, and that just happens to be the largest eigenvalue is just minus 1 over Q minus 1. Okay? This you can, it's a little exercise. The eigenvector is actually plus 1, minus 1, 0, 0, 0, 0. And it's degenerate Q minus 1 times. You can check it or ask Mathematica that this is correct, okay? In general. So this C is Q minus 1 squared. Oh, sorry, yeah, I wrote the minus here. So the stability is C minus 1 squared. So what I'm saying here is that if I initialize the belief propagation close to this uniform fixed point, but not quite at it, if the degree, average degree, is larger than that, then it will not converge back. It will converge somewhere else, or not converge at all. But it will not converge back to the uniform fixed point. If the average degree is smaller than that, then it will converge back to the uniform fixed point. Okay? Okay, so that's like this, Taule's 30 years ago calculation. So let's try to see in our graphs here, where are we? So for Q equals 3, does it get something interesting? 3 minus 1 is 2 squared is 4. So here we are getting 4. So already at 4, something gets, what we said here is not the right thing. So is it maybe at 4 that this true quenched entropy starts to be different from beta? It so happens that yes, even though at this point this is not like, okay, this is in no way a proof, but it so happens that for Q equals 3, it is exactly this stability calculation that gives us correctly the point up to which indeed the quenched entropy is equal to the annealed entropy, and starting from which it is strictly smaller because simply it cannot be bigger, and it's not equal anymore. So there is this regime where something interesting is happening. Now, what about the other picture, the large Q? Of course, Q squared is much bigger than Q log Q, right? So we are not even on this scale here in the picture. So here we still have no clue. There must be something else. There must be something else that will help us for the large Q. And also for actually any Q bigger than 3. This calculation gives you the right thing only for Q equals 3. Okay. So what else can we do? So stability didn't help us, but okay, yes?
What is the modification to the algorithm that CRISPR managed to get?
So the algorithm that Aklioptas and Moore get has nothing to do with belief propagation. That's a kind of algorithm more similar to the one I mentioned yesterday, when you just greedily assign the colors to nodes, because because you can analyze that. You see, these kind of algorithms, like think about what we can say about dynamics and physics. As soon as you have a process where spins go there and back, like a Glauber dynamics or something, I mean, okay, maybe we can say things about it in physics, but rigorously, to analyze where it converges, we cannot do anything, because this corresponds to this, like, we would have to analyze this 2 to the n by 2 to the n transition matrix, and we cannot do that, or nobody knows, right? Whereas for these processes where we just greedily assign the nodes, colors to nodes in some, with some rule, but we just do it once, these have a chance to, and these actually do have a way to write some set of differential equations that exactly describe the fraction of nodes that are assigned a given color at a given time step, and this actually is, amenable to rigorous analysis. So that's where this 4.03 comes from. And I actually thank you for the question, because that's a very good remark, right? Aren't you wondering how can it work beyond the point where this method breaks? Right? This is an interesting remark, because somehow the way I'm introducing things, you somehow anticipate that I will find some kind of a phase transition here, and then I will try to tell, okay, and there is this phase transition, and that's what causes the algorithms to break, right? But here, I found something happening here in the space of in the way what's happening in the phase space of the problem, but the algorithms, they happily work after that. And in practice, well after that. This is just because we don't know how to analyze them quite properly. So, things will not be so simple in terms of what really makes these problems hard. Okay, good. So, where are we? Okay, halfway about. So what else can get wrong? So linear stability, of course, is just, linear stability. Things can go wrong discontinuously, right? Linear stability will only tell us if things go wrong continuously. So what can we do else? So let's maybe think about, for this tree-like calculation to be reasonable, we would somehow need, so how does it look like? Let me draw some kind of a tree here. So let's see, 1, 2, 3, and 1, 2, 3. Then I would like to continue, but I won't be able to continue for long, right? So I have the root here, and then somewhere there I have the boundary. And now we said if the boundary is somehow fixed, then this iteration equations, they're exactly telling us what would be the marginals, the partition function, and everything on the tree. But so that this corresponds to what is happening on the graph, then we would somehow need these, then on the graph, the boundary connect to each other, like on a length that is bigger than this logarithm of n, right? So does it, this should somehow matter. This creates correlations in the boundaries. The boundaries are not just like arbitrary. So how can we even hope that this kind of a calculation that works on a tree and assumes everything is independent works? So let's see. So if we had some kind of a really strong correlation decay, say that the root would not know anything about what's happening on the boundary if the boundary is far away. Well, then, however the boundary is correlated, what we get here doesn't depend on what is on the boundary. So that would be one of the cases where we kind of are saved, right? If the correlation length is much smaller than when the loops start to close, then we are good, because then everything that influences us actually happens close to us, and the loops are far away. So whatever correlations the loop creates, the correlation decay killed them, so they don't matter. So let's think about it. How reasonable is it to think that the boundary somehow doesn't influence the root at all? So, can we, for instance, construct, so it's not, we can construct boundary that influence the node, the root very strongly, starting from very low average degree. Actually, starting from average degree that is about q, so much before our q log q and much before our, q, so not q squared, q, we can do the following thing. Like, let's construct the boundary in the following way. So let's put the color, I don't know, green here. And let's make sure, let's have 3 colors. Let's put red here and green here. Oh, not green, that's not allowed. Blue here and red here, right? So if we knew these guys, it is clear that this one has to be green, right? And let's continue this way. Let's make sure that we represent both the colors on the neighbors. So let's put green here and blue here, and then here it doesn't matter. And let's green and red here, and here it doesn't matter. And let's put blue here and green here, and then blue, for instance, it doesn't matter. And we go on this way, right? And this way we constructed a boundary which is compatible only with green here. And when can we do that? Well, we can do that as long as we have more colors than the degree, right? Or degree -1, but in the order is the degree. So quite soon, from starting very small average degree, we can actually construct boundary that does influence the root strongly. So maybe this is not so useful either, but then think about it. I mean, the way we constructed the boundary, we were very strict. We required that every single time that both the colors are represented here. Well, this constructed a boundary which is kind of not representative, right? When we think about what is equilibrium statistical physics, and when we think about what's a thermodynamic state, and then, in mathematical physics, we often think about we take a system, and then we cut a little piece in the system, and then we somehow, so the proper notion of how to construct the boundary is basically included in the definition of a Gibbs state. When people in mathematical physics define a Gibbs state, what do they say? They say, okay, I have this measure, PS, probability measure, and this probability measure is a Gibbs state if and only if the following thing holds, and so I choose a configuration in the system from that measure, so that will be some S, I don't know, star, from that measure. Then I erase what's inside a kind of a cavity, I just keep the S star on the boundary. Then I look at the measure that is induced in the cavity by that boundary, and with the Hamiltonian of the model that I'm looking at. And if the measure that is induced inside that cavity with that boundary equals to this one, then that's a proper extremal Gibbs state. And when you think about, how to properly define in, say, I don't know, 2-dimensional ferromagnetic Ising model, was the ferromagnetic state and was the plus state and was the minus state, this is the proper way in which you should do it. The extremal Gibbs measures are such that if you choose the bulk from the measure, then you cut a cavity, but fix the boundary. The measure that the boundary will be inducing inside is exactly the one from which you choose it in the first place. And that's the right notion that we will try to mimic here, to somehow choose the boundary in a typical way. So this is something that in math people call reconstruction on trees, and people who study physics of glasses call the point to set correlations, or reconstruction on trees in math. Reconstruction on trees in math. So we play this game that, we somehow have our test measure, what we think could be the Gibbs measure. And that's given by this fixed point 1 over q. That's the paramagnet. So the paramagnet, so we are basically testing if the paramagnet is the right Gibbs measure. So what do? Well, first we do this, we choose this as star. So that means a random configuration from the paramagnetic state. So what does it mean, paramagnet in the graph coloring? Well, we have these hard constraints that the edge cannot be monochromatic, but paramagnet means that otherwise there is no other constraint. So the process, I will keep these numbers here, but now the process is different. So we start, say, with green here, a random color here. And now we are doing the following thing, that here we are putting colors at random that are not equal to green. Right, so for instance, let me see. So for instance, we could have put in, so let's keep this one here, but we could have put in this process, red here, right? That's You know, that's possible with probability 1/8. Red, red, red is the configuration that we will choose here. So once again, the process with which we are creating the boundary is we start with a color here, and then here we put at random one of the other colors that is not green. And again, if we chose red here, here we put one of the other colors that is not red, etc., and we go up to the leaves. So this will create, for instance, this configuration, right? For instance, with red here. Okay. And now you see it's not as bad as before, because now if, for instance, we have red, red, red here, then the blue here was not implied, so maybe this one could have been green as well, and hence this one didn't have to be green, because this one, no, it actually cannot be red, and these have to be red. Well, I would have to do it a little differently, but you see that there is more freedom. Like again, from the boundary you can compute exactly what is the probability of what's happening on the root, but a priori it's not clear. And so was this the question we are asking? We are asking, given the boundary like that, what is the critical degree such that, again, if the average degree will be small, then what we will get here, down here, far away, will be this fixed point 1/q. And if the degree is bigger than something, we will get something else. And if we are getting something else, then this paramagnet is not a properly defined Gibbs measure, because remember that what we searched for was we construct the boundary from some measure and we want that it induces the same one. And then we are fine, then it is consistent. And if it induces something else, well, then we should think more. So this is the right notion that tells us when this tree-like calculation, really this naive belief propagation, really gives us the full description of what's physically happening. So, okay, so now how do we analyze this thing? Like, we can do it on the computer, right? We can create this tree, create this boundary, make it big enough, run it back, and see somehow what's happening. So that's a little bit heavy, especially if you actually want to do it with the tree, because that's growing really fast, right? It's exponentially large. That's annoying. So we actually never do that. There are two other ways to do it, and I will, okay. So there are two other ways to do it that we will do in 5 minutes, but in the meantime, I want to show you a calculation that gives you an upper bound on when does the boundary constructed the way I described, when does it actually influence the root? So we will compute the upper bound. We will analyze what is the probability that the root is actually implied. So that's something stronger, right? Because the boundary could influence the root by saying, okay, with probability 80% this should be green, with probability 10 it should be red, with probability 10% it should be blue, okay? So this kind of thing can happen, and the belief propagation would tell you. But now we will be analyzing a different process. We will be analyzing, what's the probability that actually the boundary forces the root to be green. It just cannot be anything else. So of course this is stronger, so this is giving an upper bound on whatever the belief propagation would tell us, but it's simple and we can write an explicit equation. So let's try to write that equation. So I think I can erase all this stability calculation, because, but remember it, yeah? Remember, we will come back to it tomorrow, especially this equation. Like if you are taking notes, make it colorful in your notes or something like that. But otherwise we won't be using this. We will just be remembering the q-1 squared, but that's easy to remember. Okay, so now we will, so how do I call that in my notes, this probability? Eta, okay, so one more message. So eta, ji. So, okay, let's see, or j, whatever. Let's forget about these guys here. So j, and this guy would be j, for instance. So eta j will be, so we construct the tree and we construct the boundary in this way, like randomly, but respecting the constraint that no edge is monochromatic. And this probability, J, will be the probability that J is indeed implied by above. So is implied, from above, by the colors above, or from above. So notice that if in the process that constructed the boundary we chose it green, then it can be implied only in green, right? It cannot be implied in red because that would not be compatible. So we don't need to specify in which color it is implied. If it is implied, then it is green. Okay, so how do we compute that? Well, if it is implied, what does it mean? It means that all the other colors have to be implied on its neighbors. Yes?
So you said that the statement that the boundary implies certain colors, the probability is stronger as opposed to what?
So implying the root is stronger than saying nothing at all about what the root should be. Because saying the root, so I have three possibilities. Say that green is the first color. So either the message that, if I run the belief propagation from the boundary, then this message psi looks like 1, 0, 0. That means that the root has to be the first color. Say that that's the green, right? Or it could be, for instance, 0.8, 0.1, 0.1. Okay? Or it could be 1/3, 1/3, 1/3. Okay, so this is the one that would somehow make consistent our assumption that the paramagnet is the right physical description of what's going on. So this is what we would really like to analyze, okay? So we would like to analyze the difference between this and this. When do we get the 1/q and when do we get something else? But this is harder. All that we can do is analyze the difference between this and these two. You see, so in this sense, it's stronger. What we are computing now, it will happen at larger average degree than what we are actually interested in. You see the difference? So we are, this is more subtle to treat mathematically, actually. Like, we don't have rigorous ways. We do it in physics numerically to evaluate. We just run this process that I was describing. But even, mathematically, when you want to analyze that process rigorously, actually, because this is kind of hard to, these are generic distributions, and working with these distributional fixed point equations is kind of a nightmare. Whereas here, you just reduce it to probabilities of 3 possible things or 1 possible thing, so that gets much easier to analyze. So that's the difference. Is it here? Yes? Yes. Yes, so here is, okay. Yes, here is the root. So if you want to imagine J2, so imagine that there is some I here.
So you did remove.
Yes. Oh, okay, yes. But it's, on the tree, it's somehow, if you remove it or not, it's... I mean, you could also not...
Compute the probability that, you do not, just the probability without removing those.
Yes.
What should be calculated?
Then it's the same thing. You just don't remove, you see in the equations here, all the difference is that you don't remove it here. You just make the product over everybody. That's exactly the difference between the magnetization and the message. So it's a little different. Not for the 1/q, right? Because for 1/q is still 1/q. But if it was something else, for instance, the 0.n0101, then it would depend on the number of neighbors, what it actually is the true message. So yeah, there is a subtle difference. But again, if it is this 1, 0, 0, that will not depend somehow on this again. So that's why I'm somehow putting that under the carpet. Okay, so let's let's compute this upper bound. So upper bound, where are we? So this is the probability that the root is implied from above. So if it is implied from above, then how it is implied? It's because its neighbors, there is at least one, for every color, there is at least one neighbor that is implied in that color, so that all the colors, except the green one, are forbidden on the root, right? So So yes, that's true. But that's also, so, but the way we will compute it, actually, we will write it is 1 minus something. And it is 1 minus the probability that this is not implied. And it is not implied if there is at least one of the other q minus 1 colors that is not implied on any of the neighbors, right? And now what we said that at least one of the other q minus 1 colors, so we were somehow imagining that our root is green, so the color that we choose here, let's be it red, but then we need to multiply by q minus 1 because we could have also said blue, and it would have been exactly the same. So now what is and here we want to write the probability that red is not implied on any of the k that are neighbors of the j. And here I'm not removing the I because it's the root, okay? It doesn't really matter here too much. Okay, and what is the probability that it is not implied? Well, now again, the way we constructed things is that the branches were independent. So this is just product over all the k. Of what? Of the probability that a given one of them is not implied. Okay, but what's the probability of given one of them is not implied? Well, it's again 1 minus the probability that it is implied. Right? The probability that it is implied was this eta k somehow in the generation before, like, so this would be the generation L and this would be the generation L plus 1 if you want. But remember that we only care about one given color here. Not the same one as here, but this was implied, in the color in which it was set in the process that constructed the boundary in the first place. So it's only one of the q minus 1 possibilities that counts here, right? If this given node in the construction process, we put it green, red, blue, well, then it doesn't matter here. Then it is never implied in red because it was blue in the first place. So that's why we must divide by q minus 1 here. But that's it. So this kind of a crazy thing, 1 minus okay, that's a good term. So now the only thing that we did wrong here is that we overcounted, right? Here we said, let's say that red is not implied, but we multiplied by q minus 1 because also blue might have been not implied. But what if both red and blue are not implied? Well, that we counted twice, right? So we must subtract. So what did we count it twice? So now we must subtract, we must count the term that 2 colors were not implied. So now there are how many possibilities to choose 2 colors among q minus 1 of them? That's this. Then again, this product will be the same. And this will be again the same, but here we will have 2. Because 2 out of the q minus 1 possibilities are those that we actually care about, etc. So at the end, what we wrote here is that this n at generation L plus 1 is equal to, and this is something that people like to call the telescopic sum. It is some sum like this of minus 1 power r, q minus 1 r, and this product here, j. Oh, here I forgot about, okay. 1 minus r divided by q minus 1 eta at generation before, so L. That's it. So we get this equation that describes how this probability that something is implied evolve as we are going through the different generations of the tree. And we said that at the boundary we fix everybody. So at the boundary everybody is implied. So the eta with which we should initialize this equation is 1. And then we see if it converges to 0 or somewhere else. So this, okay, now, now I still have this product here over the different number of neighbors, so we can do 2 things. Let's, for this calculation, say that everybody has the same number of neighbors. Okay, so let's just say here power d, where d is the degree, is the branching process of the tree, okay? If it is our original Poisson distribution, then we just need to average this equation over the Poisson distribution, and it's you can do it, you still end up with a closed form equation for one variable, but somehow, okay, it's easier to see if it is just a constant. So then it just gets the power d here. So what we end up here is one equation for one variable. Otherwise, the q is something that we fix and we know, and r is something that we sum over, and we sum over just q terms, right? So we can just look what is the fixed points of this equation, and what is, what we typically draw in this kind of a case is this is a eta, this is a eta, and this would be our function of eta, that is the right-hand side. So what we see is that eta 0 is always a fixed point, because if we plug 0 here, then the sum is 0. So 0 is always a fixed point. But now the question is, does the function f of eta look something like this, or does it look something like this, right? So the way we analyze the difference is that we would compute the derivative at 0, and then we would see when the derivative at 0 is bigger or smaller than 1. It's the same kind of calculation that you do in many other processes when you analyze a phase transition. And okay, we could do that. So let's, okay, that could be an exercise. Everybody would be able to do it. Let's see what we get. So where did I get the numbers? Oh, here. Okay. So let's start again with 3 colors. So, of course, for large degree, we get this situation. For small degree, we get this situation, right? For small degree, the only fixed point is 0. So nothing is ever implied. And that's the situation where we have a chance that this paramagnetic fixed point is the right one. For large degree, this can happen. Then if this is a fixed point, then this is the probability that the root was implied. And then there was, this Gibbs measure that we were testing is not consistent. So something else is happening. Okay, so what are the results? So let's go back to our 3 colors. So for 3 colors, the critical degree, so I will call it CR. So what it is already, it's somewhere here. CR is something like 4.9. Okay. So it's not, it's not giving anything interesting. Actually, for 3 colors, if we did things properly, and instead of analyzing this, we analyzed this, we would get exactly the critical degree 4, as we did in the linear stability calculation. Okay? So here, this is much bigger because there is something loose, right? We analyze something stronger than what we actually wanted. We analyzed when things are implied rather than correlated. So for 3, this is not interesting. But what about large Q? What if you expand your result at large Q? Well, then we get this. So starting from average degree, that is Q log Q, we actually get a non-trivial fixed point here. So the paramagnet is not the right Gibbs measure starting from here. And if we actually analyze the right, reconstruction process, the one where things are correlated, not implied, we would get the same, it's not the same point, but it's the same leading order behavior in Q. So both of them give us this Q log Q. Okay, so it's good because we finally got something happening at Q log Q, but we still don't understand much what it is, right? Or do we? Okay. So what to do about it? How to understand what it means? So where am I? Let's see. So how to understand what happens? There are basically 2 ways to do that. One of them is somehow the way it has been done, okay, historically, even though it's not more than 15 years ago in physics, is somehow trying to go after what are really the Gibbs states. So, here we constructed the boundary in this paramagnetic way, but we got a fixed point, which is something else. But that something else describes another probability distribution. So what if now we choose the boundary from that probability distribution? Is that consistent? It turns out that yes. Okay? So that would be a Gibbs state. So what are we saying here? We are basically saying that there are other fixed points of belief propagation than this one, and each of them corresponds to a Gibbs state. Now, how many of them are there? Is it like in the ferromagnet that there are like 3 or Q or maybe Q factorial or twice that or something like that? Or are there much more? How to deal with that? So the way that was invented in physics by Mézard and Parisi something like 15 years ago in these sparse systems, and that is related to what people call replica symmetry breaking that has been done in physics of glasses from the 80s, is basically saying we identify Gibbs states with the fixed points of belief propagation, and now what we need to do statistical physics over these fixed points. Not over spin configurations, but over these fixed points. And what will this give us? Well, this will give us all the free energies, all the large deviations, all the things that we want on the Gibbs states, not on configurations. But doing that, we will be able to compute many things. And this is why yesterday I wrote this belief propagation in this kind of a very generic way when the interactions were whatever and the spins, I didn't specify these are pot spins, these S's could be anything, it could be like continuous probability distributions, it could be what you want. Because then you can just apply this same methodology, the belief propagation, but for a different system. Now your spins are the BP messages, the constraints are these self-consistency equations between the BP messages, and now you're counting how many of them there are of a given beta entropy. So your beta entropy is plays the role of energy in that new system, and you can put there a temperature, and that will be computing you large deviations with respect to that energy, and you can do a lot of things this way. And this is what this, replica symmetry breaking version of the committee method is doing, and you get, many, many things from that. But it's a little bit hairy, a lot of computations. So that's how people did it 15 years ago. But there is one really simple and somehow way that is much more simpler to understand what's going on without actually doing almost any calculation, a part of thinking about this equation and what are its fixed points from different simpler kind of thinking. And that's related to what do I have, 10 minutes? Something like that, right? 12 minutes. Oh, I actually see it there. Great. So that's related. So let me just start this, and then I will continue tomorrow. So, okay. So just to wrap up, we have some kind of calculation that is telling us that something goes wrong with this paramagnetic fixed point at Q for large Q, and at 4 for Q equals 3, but up to that point, the annual entropy and the quenched entropy are the same. And now we want to say something about what's happening after that, and what's happening here after that. But if the quenched and annual entropy are the same, then something magical happens. And this is the following thing. So far we were talking about random graphs and coloring of a random graph. So let me define a different ensemble of graphs that I call planted random graphs. And now, these planted random graphs, I start constructing them that I have n nodes, and I have some Si star, some assignment color to these nodes that I choose at random, that is fixed once forever, before I even have any graph. I don't have any graph yet, right? I just have this assignment. And then the way I decide, I choose the graph, I say for every I and j, I do the following. Either I don't put an edge if Si star is equal to Sj star, or I put an edge with probability, let's see, C out over n, if Si is not Sj, so and with probability 1 minus that. So really how we should understand that is like this. in some kind of math notation. So if the two colors are the same, then I'm not putting an edge for sure. And if they are not the same, will just be equal to this, right? Q minus 1 C out. I just must correctly count this. So this C out is not exactly the average degree, but almost. Okay, so I will still be working at the same average degree as before. So it's this C that counts, not this C out. Just need to like change a little bit this C out to create the same average degree. Okay, good. So I have planted random graphs. So what now? So are they very different from the random graphs? Well, they are, right? For instance, this graph is always colorable because this is one coloring, right? We don't have the uncolorable regime as we did before. So this graph ensemble is not at all equivalent to the first one. It's not like the canonical, microcanonical things are the same, right? This is a different, very different ensemble of graphs. If the degree is large enough, then here we always have some colorings, and many of them, because if S star is a coloring, we always have some like nodes that are connected to nobody, or only one node that will also be able to take other colors, etc. So this is very different, a priori, right? So, people say in math, studied this ensemble and also, asked things about it, but it was only in 2008 or so that people realized that there is something magical about the planted random graphs that can be used very nicely to understand what's happening in the random graphs. And that's the following. So it's a work that, somehow the way it was stated clearly is in this work Aklioptas and Kojauglan. How is this K written? Like this. 08, so not such a long time ago. These are math people, but much after this replica symmetry breaking was worked out in physics, and they were actually working on proving some parts of this replica symmetry breaking picture. And doing that, they came with this way that is actually even much simpler to explain what's going on via this planted random graph. So what they showed is they show the following thing. So if on the random graphs we have this S annealed equal to S quenched, which we saw we have at least in a big part of the regime here somehow, right? So if we have that, then, so I will write it in quotes, then planted ensemble is equal to the random ensemble. So the precise statement is that these two probability distributions over graphs are contiguous, which in mathematics means that if a property is true with high probability in one probability distribution, it is also true with high probability in the other probability distribution. Okay, so they are not equal in the sense that their, say, like Kullback-Leibert distance would be 0, that's too strong, but in a weaker sense that high probability properties are true if and only if. Okay, or if they are true in one, they must be true in the other, and vice versa. And if you think about it in statistical physics, we mostly care about high probability properties, right? When we say the pressure is this number, what we mean is that in almost all but vanishing fraction of cases, we will see that the pressure is this number. So that's what we mean. That's what I mean by high probability property. Right? That is something that concentrates on well-defined number. So in physics, we care on things like what is the value of the entropy? Is it colorable? What is the in how many colorings this given node is what fraction of colorings this given node is red, and all properties like that are high probability properties. Large deviations are not the same, because you see, like having large degree and being still colorable is typically a large deviation property, right? And for the planted graph, it's always true, and for the random graph, it's not. So trivially, the large deviation properties are not the same. What's the high probability property? Well, for instance, how many colorings there are was the end, not the, how many, that would be, if you look, what is the 1 over n logarithm of the number of colorings? What's the entropy, the value of the entropy? Okay, if you are in a thermodynamic system, the value of the entropy will not depend on the realization of the disorder, right? That's something that is self-averaging, that's something that concentrates. It will have some large deviation, but the thermodynamic value, it will be the same for every realization. And this kind of property that is the same for every realization will be the same in the random and the planted ensemble as long as the quenched and annealed entropy is the same. So what does it mean? How do we understand it? So there is actually this kind of a sketch of the proof that they give that is actually quite, enlightening what's going on. And that's you create this like huge matrix where here you put all possible graphs. So you really have, say on n nodes and m edges. So you really have many, many graphs, right? This isn't more than 2 to the n. That's really, we are really talking about huge space. And here you put all the possible, or actually not say colorings, all the possible assignments of colors. So here you have q to the n elements, okay? And then you put 1 if that coloring is a proper coloring of that graph, and then 0 if that assignment is not a proper coloring of that graph. And you just, of course, you will have much more zeros than ones, right? And you just go on like that. You create this matrix and just fill it. Think what these two processes are doing. So the random graph is just choosing a random column. Okay, it chooses uniformly among all the graphs. Okay, fine. Now, the planted ensemble is doing something else. You first choose the assignment, and you first choose your row, and then from the row, you choose a random 1. You don't choose a random column, you choose a random 1. Column that has a 1, right? Because otherwise that assignment was not coloring that graph, so that could not be your planted graph. Okay, so now imagine for a moment that every graph would have exactly the same number of colorings. So every column would have exactly the same number of 1s. And every coloring, has the same number. Well, not quite, but okay. Let's say that that's enough. That every graph would have exactly the same number of colorings. Then these two processes would be sampling the graphs uniformly, both of them. Yeah, because then it wouldn't matter if you first choose a column or if you first choose a row and then you choose a random 1, because since all the graphs have the same number of 1s, you are hitting every graph equally likely, this way, right? So if every graph had exactly the same number of colorings, then this is trivially the same thing. Now, of course, it's not true. It's not true that every graph has exactly the same number of colorings. But if you work a little bit more, you can persuade yourself that this is exactly the same, the right kind of how much, the thing that these two things are equal, it doesn't have to be that every graph has the same number of colorings, but the fact that the average of the log is the same as the log of the average, this means is that basically every graph has about the same number of colorings. It can be 100 times more, but 100 times is still not so big. It's not exponentially times more. That would cause a trouble. Okay, so there is this magical thing that these two ensembles are actually the same. And more than that, and that's really interesting, but I should stop. But let this be the last thing I say. Because here you see on the graph, we somehow constructed the boundary that corresponded to somehow a representative configuration. So on the tree, we could somehow do it, right? But imagine that we wanted to do it on the graph. Then you somehow need to make, then you could do it locally from somewhere, but then you need to make sure that your loops here are somehow, that it's consistent. This you could not do, How do you construct a configuration that is a uniformly sampled configuration on a graph? You cannot do it with this procedure. As a physicist, you should immediately tell me, I have Monte Carlo, I can do it with Monte Carlo. But you see here we are talking about some very, anticipating some very strong ergodicity breaking with this many Gibbs states, etc. So you will be hitting phases where your equilibration time is exponential, so this is not useful either. So you cannot do it. How do you do it? And this is a magical trick how to do it. Because not only, so this would be claim 1 of their paper, and claim 2 is that S star is an equilibrium configuration. So you get a graph, and it's equilibrium configuration for free. Okay. And tomorrow we will, say what, hence we can, what can we analyze using that, and how can we make sense what's happening here? What's happening here?
In the anneal ensemble, which is the same, which would be the same.
No, so, okay, that's a good point. I'm equilibrium in which, because here we have randomness with respect to the graphs, and then we have randomness with respect, once the graph is fixed, we have randomness with respect to the thermodynamics, with respect to all the colorings. So here I mean the second one. The equilibrium here is the graph is fixed, and it's equilibrium with respect to the Boltzmann measure. Okay, I will not be using the word equilibrium to say something about sampling the graphs. I'm always thinking in the way that the graph is fixed, there's the quench disorder, and sometimes I'm averaging around over the graphs just for the purpose of compute some things. But what I actually want to understand is what's happening on one typical graph. So I always think of the graph as quenched, and I just average over it in cases where the average is just equal to the typical, or sometimes it's not equal, but it's instructive, say, or something. But the equilibrium is always with respect to the Boltzmann measure. So so it's kind of, so it's very, when you see it at first, it's very striking because, and this second thing actually doesn't even, I should not write it this way. This doesn't need this assumption. Okay, the one should be here, because this doesn't even need the assumption. For the planted graphs, it's always true that S star is an equilibrium configuration for the Boltzmann measure over all the proper colorings. That's always true.